Hi, I'm going to commit an unforgivable sin and now give a fairly technical talk at the end of the day so that you can all feel you've earned your wine. But what I'm really doing is telling you a little bit of a story about the parallel development of an optimal algorithm and the data science that really let us be able to do what we wanted to do to be accurate in a way that wouldn't have been computationally feasible if we had just tried to brute force it, right? So this is really about the back end of data science. You know, we often talk about customers and understanding the user and understanding user preferences and the kind of externally facing insights from data science. But what I'm going to talk about is on the back end, how do we use data science to enable companies that operate at this huge scale like Amazon or Google or Walmart or any of these folks you've heard from today, to use algorithms that we wouldn't be able to use at that scale, even with our computational power, by being more intelligent about it and having a good starting point. Oops. So I have to first explain how a search engine indexes the web to give you the context for this problem. So it may be old news, but there's no complete enumeration of the web. And the reason we talk about crawling the web is that a long time ago, people said that you spidered the web by following links from one page to another. And that's how a search engine actually identifies new content and how it finds, new combinations of words and phrases. So what happens, right? You go from this dynamic web that exists, that's updated everywhere out there in the world, through what we call an indexing pipeline to create an offline repository. What that functionally means, and those of you who've messed with this before will see notation about term frequency and inter-document frequency of terms. And what a search engine does is it creates not really a copy of the web, but it pre-processes web pages that it finds when crawling the web and creates effectively a database record, which it can access very quickly based on the terms that you enter, the type of content that you're looking for. And of course, this task gets more complex as things like Twitter arrive and structured data and real estate websites that are generating new kind of listings and content on the fly, right? So this is about pre-understanding the data. And if you haven't pre-understood and pre-processed this page, there's no way that when someone types in a search term, you can actually find the page quickly enough to be useful to them, right? So how do we handle updates to those pages, right? Because we just talked about a few really dynamic types of content like tweets, your Facebook profile, new real estate listings, new Craigslist postings. So getting hold of these updates is critical. But we have this whole web that's updating, and in some cases you will get feeds of data from CNN saying new article, right? This is old school and RSS feed. Those of you who use some kind of reader combination will be familiar with this idea that some blogs can actually push those updates at you in a structured way. But generally speaking, if you're taking a course at Stanford and one of your professors goes out today and creates the syllabus and you're a student and you type in CS 206A, you're expecting to get the course syllabus, right? But somebody just made it this morning because it's the beginning of the term and stuff is getting created all the time and never updated again, mind you, I'll tell you. So there's a lot of stuff that's critical about keeping that content fresh. There are direct changes to content. There's inferring timeliness, because remember, this is a huge learning problem where we need to see the co-occurrence of certain words in news events to understand that those things have a new meaning in context today. There's also link changes, people linking to new content because we have no list of what's on the web today. And there's what we call signal propagation. So algorithms like PageRank need to actually see those links in order to have the correct signal for that page's quality. So this all takes computation power. We want to get these updates, and Google's always talking about how we have these huge data centers. I've actually seen the one that says 1997, and it's not that impressive these days. But I think the index had 200,000 pages in it, which was huge at the time. And they're sort of 2005, and then now Google puts out these nice colorized maps that you should look at on Street View if you haven't seen them. But the main thing that you get from them is, wow, these things are really big. But I'll tell you something, compared to the web and everyone out there in the world updating the web and all the automated processes, they're not that big. So even if you could brute force processing the web addresses we see, we found something like 60 trillion web addresses. Now, 70% of them are going to be duplicates, but with unique URLs. But we've indexed over pages from over 230 million domains, and the web just keeps growing, right? Some of you are going to go out today and write a new blog. And if everybody does that, there's no way that anyone wants to build the compute power and cover the earth with disks or pay for it, assuming you were willing to build it. So just to give you an example of why this problem is challenging, we see average document sizes, so 1 billion documents is something like 20 terabytes. And a home internet connection for calibration can download about 2 megabits per second, or 12.5 documents per second. So if you try to download these over a home internet connection, you're looking at something like 926 days to get this chunk of data down to where you are. And this is sort of a two-way problem, because you also have to deal with how fast a small website can give you the data. So most businesses have a comparable connection to a home internet connection with their hosting service, so you just can't get this stuff, right? Even if Google was willing to take it, you can't get it from the web. So the goal here is to be efficient. And so the first step, and I'm going to go through some technical stuff, but really this is kind of the example, is to identify content that's likely to change. So on the top line, we have our URL. And it's blue, this is time going to your right. It's blue when the URL updates, and it's red when a crawler sees it. So in the first line, we have a crawler that's crawling at intervals 1c, and then we have a crawler that crawls at intervals 2c, and you can see when it's going to pick up the changes from that page. Because we don't know exactly when the page changed, we only know what we see. So if you think about this logically, you can average the number of changes that you observe over the time, and you could get an estimate of how often this page changes. Okay, so it's not quite that simple, because as some of you will have noticed from the diagram, our data is censored. So we only see changes when we arrive at the page. There may have been 2 changes, or 7 changes, or 156 changes in between the time we saw the page, and so we'll actually introduce bias into our estimate as a result of how often we crawl. And that's not ideal, right? And then the second issue is that our crawl samples are irregular for the same reason that we just explained, which is people's connections are spotty, they're slow, you can request an update from a particular website, but you may not get it back this time, you might get it back 80% of the time or 15% of the time, right? So you're never going to have a perfectly regular sample, and believe me, I've tried. I think we got to about 85%. So there is actually some work around this, finding a maximum likelihood solution for this, and I've described the equation there. You can use this MLE to estimate an unbiased estimate of change, and this seems like a perfectly good idea that's covered in a paper, and we tried it. So what now, right? The first problem that you encounter is that most of the work that's been done on this subject, and this is where the data science comes in, has been work that works off a test corpus of pages, where you have a history of changes. My problem is that I'm going into the future, right? So I see pages being created every day, and I have to then schedule them for future crawls. And the maximum likelihood estimator that we just saw is undefined when a page has always changed or never changed, which is after the first time you see the page. So I need to estimate the moment the content appears. And if you parse this drawing, which shows you a bunch of different crawl samples for a page with a true average rate of change of every 24 hours, if you start with a 30-day initial crawl interval, you'll actually have to crawl the page 15 times before you will see it change, if you just gradually keep ratcheting down your estimate, right? And this is a lot of wasted effort when that's a trade-off for me in terms of the total number of crawls I can do and what I want to do with them. And if you've got a couple billion pages, then you start to worry about that. So this is where the data really comes in. what you observe here gives you leverage against this type of algorithmic problem. That different types of content, different types of hosts have radically different distributions of update rates. So on the left, you'll see a sample of 10,000 pages that I have a pretty good idea of what their average rate of change is. It's a histogram. So you can see that the largest buckets are pages that change less than every week. So there's a lot of content. But if you look at the proportions, you're really, not looking at 90% of pages. There's this really long tail of pages that have a fairly well-defined update rate, but it's 62 days on average, right? Which means someone probably tries to get to it once a quarter or something like that, right? And you can also see even more finer-grained changes. On the right, you see a distribution of change events. These are the pages that we painfully tried to crawl every single hour for like 2 weeks. And you can actually see that different languages have very different appearances. So this is the time of week in Pacific Standard Time. And the red line shows the update rate for French, Italian, German, and Spanish language pages. And the blue line shows the update rate for Chinese, Japanese, and Korean pages. And the first thing you see is that not all these pages are in Europe, but the European webmasters have a much more tightly defined workday than some of the other languages. Now, some of this is, of course, the spread of time zones that you're dealing with and so forth, but it's very hard to tell whether a page is being updated from the sort of natural country association of that language or from the US, someone working in that language. So this gives you a lot of leverage, right? Because what I'm going to do with this is fairly straightforward. I'm going to observe that for any particular page, I can, say for high PageRank pages, pre-create a database of prior distributions, right? Where I can say high PageRank pages tend to look like this. Pages which are French, which are on this particular host, which are created during this time window tend to look like that. And I can use this to actually fix some of the problems of my maximum likelihood estimator, right? I'm going to apply this prior to the existing likelihood that I defined in the MLE calculation and get an empirical Bayes estimate, which solves two problems, one of which you'll have to take my word for. The first is it's defined everywhere, and the second is when you actually calculate it out, you need far fewer initial crawl intervals to arrive at an approximately correct estimate. More on that later. We create, however, a new problem for ourselves, which is this estimate is too expensive to compute because there's no closed-form solution due to our censored data. And we cannot afford to empirically maximize a likelihood for every single one of these pages. So it turns out that if you're a data scientist, you come up with a little trick, which is that you can use simulated annealing to come up with some fake data. So every time you see a new page, you have a lookup table that says this page has this prior, which is represented by these two fake data points. And if I enter those two fake data points into my really nice binary search solution to that MLE as the initial values, I get something which looks, a posterior likelihood, very similar to what I wanted to get by empirically maximizing the likelihood. So basically what you do is you use the data to create some leverage for yourself so that you can use this algorithm you wanted to use but was too computationally expensive. So we can be right but cheap, which is what my boss likes. So the third step, and I won't really get into all this today, is if we know the true rate of change, how often do you crawl the page? What we've talked about up until now is estimating the rate of change and pretty much crawling it on that rate. But the reality is if you think about the Poisson distribution, that's not what you want to do. Because if you crawl it on the average for the Poisson distribution, you're going to spend a significant amount of time having the page be what we call stale, where the live version does not match the version that you've indexed, because this distribution has mass on both sides of the mean. So when you realize that, you now have an additional problem, that what you want to do is figure out what your comparative cost is between the average freshness you want to target, how often does the page match the live page, or how often do you catch an update to the link structure, versus how often do you waste a crawl. And now you've created an optimization problem for yourself, right? And a way to make this decision. So if you're interested, this gives you the formulas, but what you really see is that you now have another data problem, that you want to value the cost of a crawl. Well, you can do that based on how your system works and how you want to optimize, but you also want to value the cost of a page being stale. How likely is this page being stale to actually impact your users? Is this a page that gets viewed very often? Is it a hub on the PageRank graph? Does it have some high value? And what this graph shows you is that you can look at the increasing cost of a page being stale for an hour on the bottom, and the increasing cost per crawl. And these lines give you the surface, which says if your cost per hour stale is 10, and your cost per crawl is also 10, then you want to crawl this page at about 40%, 35% of its average rate of change. And then the real business question becomes, how do you value these things, right? And that's something that you can actually answer in a kind of business context, right? So you've created an optimization problem that you can hopefully solve, or at least come up with some, basic principles, right? And I think this is a really great illustration of why data science is important in both, understanding what your business is, but also in operations and how you actually can get the features that you want in a recommendation engine or in a search engine that you wouldn't be able to fit in before. And I think the key element is understanding where we can do better, right? Having faith that we can do better, which I feel like is a big part of what I do at work in data science, but also finding those areas where the data gives us information about how we can leverage the system that we wouldn't have otherwise had. And the other thing is that at scale, at the types of computation we're talking about, I go out for a year for 1% on Google's data centers. And I think there's often a tendency to write off those types of work as, that's statistics, or that's, computational math, and that's, not a user-facing feature. But when you get to, can you make these types of problems work, 2% or 5% is a really critical difference between being able to do the features you want in a search engine and not being able to do them. And I think this also comes down to something that a lot of us learned who came out of a PhD program, that finding the right algorithm is only part of the problem. Even with the right solution from an algorithm standpoint, you have to figure out how to make it work in practice. And data science going forward is a big component of how that happens. That's
what a great place to stop here. Thanks so much, Carrie.
Sure.
Okay.